interesting stuff. So what happens? The helicopter, he said, as long as it's isolated from ground, they can bring themselves up to the potential of the wire. The wire is roughly 500,000 volts. So that's what he does. He reaches out with the rod, and it arcs while the charge is transferring, and it bringing the helicopter up to the same potential as the wire. Then he puts that clip on there to keep them at the same potential while he's climbing onto the wires. And then what happens when the helicopter wants to fly away, there's some arcing almost immediately. So the helicopter really loses that charge very quickly because probably all the air blowing over it is picking up some of that excess charge and taking it off the helicopter. It's losing that charge very quickly. The suit, 25% stainless steel thread, so he's got a Faraday cage around him. Why does he need a Faraday cage? There has to be a potential difference for you to get a shock. So I'm not sure why he needs the Faraday cage. I think it's for getting on and off the wires. Right? That's a dangerous time when the arcing is going to the helicopter's at a lower potential, the wire's at a high potential. An arc might go through him to the lower potential helicopter and shock him and kill him. But once he's on the wires, he shouldn't need it. Right? It's like a bird landing on a power line. It should be fine. It's isolated from ground. And it arcs to the end of that rod, right? We'll talk about that in a minute. Pointed conductors have very high electric fields. That's where the arcing usually takes place. If you don't want that to happen, you have to have nice, smooth, radiused metal edges. Pointy edges are bad if you don't want high electric fields. Sometimes you want them, right? Like in this case, he wanted the arcing to take place on that rod, so they knew where it was happening. So you'd use a pointy rod. Okay, so an interesting video with the suits, the Faraday suits. All right, let's go back to just a quick recap on the electroscope and how the conductors, where the charge goes on conductors, and then we'll get back to electric potential, the next chapter here. So real quickly with the electroscope, what did we do? We had that's all metal. It's connected to this, and there's a rod in here that's connected. All electrically connected together. This is all one conductive surface, really. So the rod in the center there hangs vertically, and we bring a charged object up next to it. And let's make it positive charge. So what happens when we bring a positive charge up next to it? The electrons can move around in this conductive material, and they are attracted up to the upper surface. So we get electrons moving up. And what does that leave behind? Leaves behind some positive charges. And positive charges repel each other. So what's going to happen to that needle? It's going to rotate, right? And that's what we saw. So what happens if we ground it now? We've got our positive rod. We've got our electroscope. And we reach in and ground that's a symbol for ground. You know what grounding it means? It means that we are attaching it to a huge reservoir of charge. So if this object wants more electrons, it can get them. If it wants to get rid of its electrons, it can get rid of them. It's just a huge reservoir of charge. That's what ground is. So in this case, what happens when we ground it? We've got a positive rod hanging over it. So does it want more electrons, or does it want to get rid of them? It wants more electrons, right? Because there's a positive rod there attracting them. So more electrons are going to flow in. And when they flow into the electroscope, there's a need for some extra electrons in the bottom. Since we have this unlimited pool of electrons we just connected it to, some are going to go down here. And some are going to stay up here probably. We might get some extra ones, right? Because that positive charge is going to attract some there. So what's going to happen to that needle? Let's see what happens. Okay, so the needle turns over. We ground it. And then I take the rod away. Is that what you expect it to happen? Let's look at it over here. Okay, so the needle moves. I ground it. And I take the rod away. So when I grounded it, extra electrons came in. Some of them came down in here because there was a need for some electrons there, right? We had a net positive charge in that area. And the needle went back to vertical because there was no charge difference. And we probably got some extra electrons up here. Well, we did get some extra electrons up there. Then, since the ground was removed, and my object, our electroscope here, now has excess charge, right? Remember, it started out, it was neutral. Now it has this excess charge. There's our it's in this is the situation right after I removed the ground. Excess electrons went down into the lower part and have sort of canceled out with the positive. So this part's neutral. And any excess electrons now are up in the top because that's where the positive charge is. And now when I remove the positive rod, what do those electrons want to do? Get as far apart from each other as they can. So when we remove the rod, these electrons spread out. And the rod rotates because now like charges repel each other. Did you follow that? So this is one way we can charge an object. Right? We talked about rubbing. Rubbing was one way. This is another way. We can ground it while we're holding a charged object near it, if it's a conductor. That works if it's a conductor. So this was maybe a complicated example, but let's look at something, a simple example, where we've got just a sphere. And so it's going to have no net charge on it, right? It's neutral. And we bring in a charged rod. What charge do you want it to be, positive or negative? Huh? Negative? Bring in a charged rod. And so what's going to happen? The electrons are repelled, right? They want to get as far away as possible from that negative rod. And if we bring in a ground, what's going to happen to those electrons? They're going to leave. So if we remove the ground while the charged rod is still there, that's the key. The charged rod has to be there still. We remove that. Now what happens? We've got an excess positive charge on our sphere. Some electrons have left. And now when we remove the negative rod, they evenly distribute themselves. They try to get as far away from each other as they can. So they are going to distribute themselves over the outermost surface of our sphere. So our charge is now negative. We have a net charge. We didn't before, but we do now. And if you had a positive, what would happen? It would have attracted electrons in. And as long as you remove the ground while the charged rod is still there, you now have a charged object. What happens if you remove the charged rod first while it's still grounded? You get right back to where you started, because your object has a net charge, right? So here we could draw it out. You have a charged rod. You ground it. So some of the electrons went down there, right? And we have a net positive. And now you remove the rod. So the net positive here is going to attract electrons. Electrons are going to be attracted to those, right? And then what happens when you remove the ground? You're back to neutral again. So in order to charge the object, you have to keep the charged object. In order to charge the sphere, you have to keep the rod, the charged rod, there when you remove the ground. So the electrons leave, you remove the ground. Now it's isolated. It can't get any more electrons. It can't lose any more. And then you remove the charged object. Question?
Why is the one above the negative net charge with all the electrons left?
That's a good question. Thank you. Net positive charge. Thank you. Yeah, the electrons leaves positives behind. Thank you.